Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video for you all. And of course, today's lesson topic is going to be a new one, something that we're moving further along into after our Conic Sections unit. This is all about geometric reflection, so utilizing all of what we've learned into different concepts, applying these previous knowledges into these more complex problems, and of course, looking at it in an overall different perspective, some more real-life applications as well. So today we're going to be looking at object generation and cross sections. So these are two very important topics and lessons within this unit of what I just talked about, geometric modeling basically on Earth with reality and real life objects, not just objects on the plane and not just objects on your paper, not just figures, something that we can correlate to and look into actual career applications as well. So the whole entire purpose of our lesson I will get into after. Of course, you make sure to smash that subscribe button down below, hit that like button on this video, and turn on post notifications so you don't miss out on any of our channel's latest uploads at eCoreAcademy, and so that you're always up to date with all of our lessons and you don't fall out and you don't miss out at all. So what's the whole theme and underlying message that I'm trying to get across with this specific lesson? What we're first going to do is we're going to look at what cross sections are and also what object generations are, and how exactly cross sections can be discovered, and how can object generations be discovered separately, and also how they coexist. So we're going to be looking at how cross sections can be discovered and discovered and represented through object generation. So without further ado, let's jump right into it. All right, starting off with our first slide, we have our introduction. This is part one. I'm going to split these introduction slides into two different separate slides pertaining to our object directions and our cross sections. But for this first slide, we're going to look at what are cross sections. What exactly are cross sections, and what do they represent? So a cross section is when a plane intersects a three-dimensional figure, such as a double-napped cone, and it forms two-dimensional objects. So if we take a look at our plane here, we're going to have a plane which is a two-dimensional outlook on any 3D outlook. You can think of it as some sort of parallelogram. In this case, we're going to look at it in a rectangular parallelogram form, but it's just that entire two-dimensional plane on a three-dimensional overall outlook. So that has to correlate with, of course, our 3D objects. And it's going to intersect this three-dimensional figure, this 2D plane intersects this 3D figure, such as our double-napped cones in developing our conic sections. But this is more of a universal concept in which you can utilize it for any types of three-dimensional figures, not just your double-napped cones. And it's going to intersect that 3D figure to form a 2D figure, actually. And you will be tasked with discovering the area of that cross-section when you're given the properties of the object. So given, such as, say, for example, it's a prism, you'd be given your length, width, and your height. So you have to utilize the given information of your length, your width, and your height in order to develop, your thesis and, of course, your actual answer for the area of your given cross-section, because it's a 2D figure that you're actually forming with the cross-section of a 3D figure. So I'll give you some real-life examples. These are some very interesting examples. So right here, we actually have an amoeba cell. So we know that cells can be looked under a microscope, and none other than a microscope. They cannot be visualized with the naked eye. But something that we know about cells is that we don't always see the full shape of it. A cell is a 3D figure. It's an organism, and it's an existent organism, and anything that's living is automatically going to be a three-dimensional object. Now, one thing that we always look under the cell, under our cell microscopes, is we always see this right here. We always see this little picture right here. And what this is really indicating is a cross-section of your given 3D amoeba, or your given organism. And all a cross-section is when you take that given plane and you're almost slicing out a chunk of any figure, and you're taking what's shown on that very frontal part of that chunk, and you're basically putting it out flat like a 2D object with no depth. And that's exactly what this is. This is length and width representative, no height. So it's not volume, it's area that you're calculating. So this is a cross-section, something that you cut out of your given amoeba cell. And then another example would be a tree trunk. If you're taking a 3D object like a tree trunk, you're cutting through it, and you want to see what a cross-section looks like, you'd be using your plane as sort of that mechanism. You'd be cutting through it, and then you'd be developing this whole entire two-dimensional outlook of that 3D figure. So that's another example of your cross-section, and both these are very important in determining, say, for example, for the cell, you would want to know the interior counterparts of your cell, how it's actually going about its general processes, and what it looks like on the inside. And then also with your tree trunk, you can utilize the tree trunk to actually tell a tree's age, whether or not it's aging, if it's healthy, if you need to chop it down, things like that. All right, moving on to introduction part 2, and this is all about rotated figures and object generation. So this is object generation is through rotated figures. So rotated figures are the figures that develop your actual object generation, and they are developed by the appendicular or axial rotation of a two-dimensional figure around a given axis to form a 3D figure. So this is kind of your opposite, opposing counterpart of overall 2D, 3D interference. So when you have a three-dimensional object and you're trying to develop a 2D object, just remember it always has to do with cross sections. So you're cutting out a certain amount of that 3D object, and you're actually going from more to less to actually find that 2D object. But rotating figures is the complete opposite. You're going to be taking a given two-dimensional object, say for example a square, and all you're going to be doing is you're going to be rotating it around a central axis. And when you do so, it'll connect entirely, or you'll stop halfway with a given certain degree rotation, which I'll get into in the end of this video when we cover our rotated figures. So stay in tune for that. But basically all it's doing is it's rotating a given 2D figure in order to give it depth and make it a three-dimensional figure. So it's going from less to more, from 2D to 3D. And you will need to know what types of figures are made by a certain degree of rotation. So if you're given a given figure, such as a square, and you're given that it has to rotate around a central axis, you have to be able to tell what type of figure it's going to develop. Maybe that's a drawing, or you have to identify it with another correlating picture. Very simple stuff. Just you have to have that general knowledge, and that's just geometric skill that you're going to develop overall. And you're also going to need to know their properties. So you'll get a lot better just through identification and just through practice. So another real life application of what exactly I'm trying to show you is this implication of gift wrapping. I know right now when I'm recording this is the day before Christmas, so I thought why not include that, gift wrapping. It's a very important part of Christmas or any gift giving process or holiday. And we know that gift wrapping, it's a two-dimensional figure. We can think of our gift wrapper paper as a 2D figure. And all we're doing is we're wrapping it around that given gift in order to adjust it to make it a 3D figure, a 3D appearance, rotating it around multiple central axes. So what I mean by appendicular and axial rotation is axial rotation has to do with your up and down axis. So say, for example, this is an axial axis. And this is when your figure is going to be rotating around this up and down vertical axis. But an appendicular rotation would be when you're having an axis that's actually going sideways, an appendicular rotation. But it's going to be in the same manner. It's just a rotation of the other, so it's going to be rotating around this way. Just like that, same direction. You're always going to be going in a clockwise manner, actually, or a counterclockwise manner, depending on which way is specified. So if it's a positive degree measure, you're always moving clockwise. If it's a negative degree measure, you're always moving counterclockwise. All right, let's continue and let's actually get into some problems. This is a much more problem-based video, like I was saying with this whole ending unit for geometry. So this first type of problem that we're going to come across is practice with prisms part 1, and we're going to find the area of the cross sections of these rectangular prisms. I'll write that out here for you. Rectangular prisms, and of course this is a representation of a three-dimensional rectangle essentially. So what we're given two different cross section scenarios. So this is our first cross section and this is our second cross section. So first thing that I always recommend doing is we have these giant planes that are intersecting like this. These are our giant planes that are actually cutting out, I'll just star that here. This is our plane and this is our plane right here. They're intersecting your given rectangular prisms. But something that I always like to do first is that plane can be quite annoying sometimes, and you might not exactly be able to specify what exactly you're looking for. So I always recommend draw it out. Whatever you do, always draw out what your cross section might look like. So we know it's a rectangular prism, and we know that it might not have a square base, so we're going to give it benefit of the doubt, and it's not. I'll give you the length and width and height, but I just want to draw it out first. So we're going to draw out what it looks like. So this is what it most likely looks like. This is an estimation, something that we can get to that looks like a rectangular prism. And then of course here it's going to be a bit different. It's going to be a lot longer. It's going to be a lot longer, this one. So it's going to be more of like a vertical tilt because we know these cross sections are happening at different places on the same exact rectangular prism. So and of course these two are going to be congruent to each other. So what I'm going to tell you is I'm going to give you some information. So I'm going to tell you that the length of these two prisms is going to be 4 inches. I'm going to tell you the width of these prisms is going to be 5 inches, and that the height is going to be 12. So we've given ourselves the dimensions of the volumes of these prisms, but now we're given cross sections, and we have to actually calculate the areas of each of these separate cross sections. So with the given information, we're going to label these rectangular prisms. So we know that our length is 4 inches. So this guy right here is going to be 4 inches. We know our width is 5 inches. So this guy right here is 5 inches. And then we have a height of 12. So let's label this guy, this long piece right here, are 12 inches. So what we're going to do now from here is we're actually going to calculate the area of our given prism. So we know that with prisms, in this case, our prism is intersecting such a way that it faces the base. So since we know that it's directly intersecting in a perpendicular manner and it's facing upwards to the base, it's actually going to have the same exact area of the base. So in order to calculate the area of the base, we don't need the height. So we can X out the height. We're given the dimensions of the length and width, and that length and width actually represents the dimensions for the area of the base, which is then the area of this cross section. So we know that this base area here is going to be 4. So that's going to be the same as here. It's going to be 4 inches. So let's label that here. So 4 inches. And then we have our width here, which is 5 inches. So that's also going to be 5 inches here in our prism. So let's label that 5 inches right here. Let me move this out of the way. Area. We already know what we're looking for. All right. So what we're going to do here is our basic length times width. So we have 4 times 5 because this is a rectangle. So 4 times 5 equals 20 inches or square inches. Yeah, 20 inches square. And then, of course, we have our second cross section here. We know that our length is 4 inches here. And we know that our width is 5 inches right here. We also know that our height is 12 inches. Now, this time it's a bit confusing, but we know that a rectangle always has 2 different types of faces. You have your top and bottom base, and then, of course, you have your side 4 bases. So in this case, we're actually looking for the side bases. We're looking for one of the areas of the side bases that's going to be representative of the area of the cross section. So let's take a look here. How exactly would we calculate the area of this cross section on one of these bases, these side bases? Well, we know that we need to know a length and a width, but the length and the width of the rectangular prism is not what we're looking for. We're looking for the height and, of course, the width as well. So we know that the height is 12 inches because this is going in a vertical manner. So the height here will be 12 inches. So that's one value that we need to know. That's a long piece right here. It's going to be 12 inches. And then we also need to know what the width is. So the width here, we know it's 5 inches here. So we can just write that value up here, up top, which is going to be the same for our cross section as well. So know that that's 5 inches right here. And we're going to do the same thing. We're going to multiply these values together. So 12 times 5 equals 60 inches squared. All right. Now moving on to the next problem. That was quite easy. I just wanted to really break that down. But now we're going to assume that we already know some of these steps. So if you're confused, please rewind. And of course, I'll have an extended problems video on this as well, probably posted by the time that you're watching this video. If you're watching this a lot later than when I actually posted this video, you can always refer to that. But we're going to move on to the next problem. So this is practice with prisms part 2, and we're going to find the area of the cross sections of these 2 pyramids. So these are the same pyramids. So I'll write that these 2 pyramids are congruent. And all we're looking for is the area of this given triangle. This given triangular prism is shown in the center. So I'm going to give you some values here, and you're going to be able to calculate what those values are and actually calculate the area of your cross sections. So first off, let's start off with our first step. What I'm going to tell you is we're going to start off by drawing what this cross section will look like. So since this is a cross section, you're taking your pyramid and you're dividing it straight through the vertex in this manner, you're going to find a triangle. That's going to be your automatic go-to. It's always going to be a triangle whenever you're dividing it on vertically. Whenever you're dividing it horizontally, it's always going to be the shape of the base. In this case, it's going to be a square, but it can be a rectangle, whatever the shape of the base is. So this right here is going to be that slant height, that slant face. So this is going to be a triangle. So let's draw that out. All right. We have our triangle drawn out, and then we're going to draw our square out, estimating, giving it approximate. I want to make that as even as possible for the square. Okay, that's our square right there. So those are our 2 different cross sections. So some information that I'm going to give you for this triangle. So one piece of information that I'm going to give you is the slant height. So this is the slant height right here. This is going to be one of the sides of the triangle. So we know that this is a square triangular prism. So we know that these two sides are going to be congruent, and that this side will not be congruent. This will be a different length, of different length. We'll assume that this is of different length. So when we're given this triangular cross section right here, we're given that our slant height is going to be 12 inches. So I'll write here slant height equals 12 inches. So we know that our slant height is 12 inches. And so we know that this is going to account for this side of our given triangle right here of our cross section. So what we actually need to discover here is the area of this entire triangle. So what we're going to do here, since we know this situation, this is a very common situation to come across, we're actually going to utilize some methods that we do know. And I'm also going to give you the base of this whole entire triangle. The base of it, the distance across this square here, base, equals 5 inches. So if we know that our base equals 5 inches and then we know that two sides equals 12 inches, we're going to have to find the area of this triangle. So if we know that this is 5 inches, we're going to divide this triangle in half, actually. So when we divide it in half, we're going to get two pieces of 5 inches that are going to equal 2.5 and 2.5 inches. So 2.5 inch and 2.5 inch. And then what we're going to do is we're going to actually multiply our 2.5 by our 12. Not multiply by our 12. We're going to utilize 12 and 2.5 in the Pythagorean theorem to actually calculate what this given height is so that we can multiply by 2.5 to calculate the area of this triangle. So we know that 2.5 squared plus b squared equals 12 squared. So we know that 6.25 plus b squared equals 144. We're just simplifying this out, so we're going to subtract 6.25, so 144 minus 4 is 140, and then you're going to subtract another 2.25, so you're going to get 137.25. So b squared equals 137.25, and then we're just going to square root both sides, and we get that b equals the square root of 137.25. And since we know that our base here is going to be 2.5, we're just going to say that our final value is going to be 2.5 root 137.25 for our area, so inches squared. That's going to be our area of this guy, this cross section right here. And now for the square cross section, I'm going to give you some other values as well. So what we're given is that the distance between the vertex and the actual square itself is going to be so this lateral height, this distance right here. I'm going to draw that out. So this distance from the vertex of the pyramid down to the actual square, any part at the center of the square is actually going to equal 6 inches. And we're also given that the total height of this entire pyramid is going to be 12 inches. So this total height, is going to equal 12 inches. And another piece of information that I'm going to give you is that the length, the side length right here of the base is going to be equal to 4 inches. So with that given information, you have to be able to decide what the area of the square is and develop a formal process in order to discover that area. So what we're going to look at here is we see that we have a height of 12 inches and a total height of 12 inches, and that we know that the square is 6 inches from that vertex. So basically that cross section is going to represent your base of your pyramid. However, it's not going to be the same area. One thing that we know about a pyramid is as soon as you make a horizontal cross section and you start moving up the pyramid, that square is going to decrease by a constant amount until it goes all the way up into a single point. So this square right here is going to be way less than your given base. But yes, we can discover it through proportionality. So we know that our height is 12 inches, and then we know that our 6 inches is going to be representative of the difference between the point and that given square. So we know that our ratio is actually going to be 1/2. So we're going to divide our given length here, 6, by 12 to get 1/2. And we know that that central square, because it's half the distance, it's going to be half the area of the base, if that makes sense. So we're going to divide our 6 by 12, and we get that it is 1/2, or 0.5. So now we can go to work. We know that our base area is going to be 4 inches. So we're going to multiply 4. 4 squared is going to equal 16. That's the area of our total base, 16 inches squared. And all we're going to do is we're going to multiply 16 inches squared by 0.5, and we're going to get 8 inches squared. As simple as that. And so our values here, it's actually going to be root 8, or it's going to be 2 root 2. So that's going to be our side length values. Yeah. Okay. Yeah. So that's basic overview of a pyramid. I know that was a little bit complicated. That's probably the most complicated problem. So I really wanted to take time to digress about that. And so if you have any questions, please look through the entire video. I'm sure many of your questions will be resolved in any of these upcoming problems. But please pay attention, and we'll get through this video, pretty efficiently and pretty quickly. All right, practice with prisms part 3. Let's this next cross section, which is a bit of an easier problem here. I'm trying to relax a bit on that and kind of diversify the different problems that we're going across. So right here, I have a triangular prism, another triangular prism. It's not a pyramid, however. This is a unique triangular prism. And one piece of information that I actually want to give you is that our prism here, this base right here, is going to be an equilateral triangle. So that all sides are going to be congruent. So something that we know here is that our base is going to be congruent here, and this is our given cross section right here. So it's already drawn for us, but let's etch it out again. So etch this out, try and make it as even as possible. These are 3 congruent side lengths. And what we need to do is we have to calculate the area of that given triangle. So one piece of information that I'm going to give you is that this base right here is going to equal 8 inches. That's the area. That's the length of our. Actually, let's switch up our units of length. Just kind of diversify it a bit. So let's say 8 meters. 8 meters of length. So we're going to try and calculate the area of this entire cross section as shown, this rough sketch here. Let's utilize that and label our dimensions what we're given. So we know that our 8 inches here is going to be representative of the base. Because the cross section is facing the base, it's going to be the same area as the base because it's a triangular prism and not a regular pyramid. So that's the difference between prisms and pyramids, prisms and regular pyramids. So we're given this value here, and what we need to do is we have to actually calculate the area. But one really cool thing that we know is that this is an equilateral triangle. So we can utilize our special right triangle properties. So what we're going to do is, let me clear out this these angles here and draw this out. So what we're going to do is we're going to split this equilateral triangle in half down the middle through that vertex, that central vertex, all the way down to the base. And when we do so, we're given these 2 congruent. One second. Let's make this nice and straight. All right, so we're making our 2 congruent triangles as shown. Now, when we do that, we know that we can utilize our 30, 60, 90 triangle property. 30, 60, 90 triangle. And what we're going to do here is we know that we're given our 8 inches, so we know that this is actually going to equal 4 and 4. We're going to focus on this side. So we know that the relationship between these side lengths are going to be, this is going to be root 3 times 4, and this height here, this guy right here, this hypotenuse is going to be 2 times 4, so 8. And we know that the height is actually going to be root 3 times 4, so it's going to be 4 root 3. So if we know the height, all we need to do is multiply the base times the height. So we have our base of 4 here and our height of 4 times root 3. We're going to try and calculate what the area of this triangle is here. So 4 times 4 root 3 equals 16 root 3. And the thing is, we don't have to divide by 2, because the thing is, if we divide by 2, we're only going to get the area of one triangle. However, if we leave it as is and we don't divide by 2, we're actually going to account for both areas of both triangles because they're both congruent. So overall, our entire area of this entire cross section is going to be 16 root 3 inches squared. And always leave it in radical form unless otherwise specified. Radical form always gives you an exact answer, but you can always plug that into a calculator if you want to get an estimation. All right, moving on to the next problem. So now this is practice with conic sections. I wanted to really change this up, and this is a much more complex problem, similar to that complex pyramid problem. And that's exactly what we're here for. So this is a sphere as shown. I'm just going to label that. And this is going to be a cross section of a circle. So a circle is a conic section. So as we look here, we have our conic section as shown. It's your regular, circle off of a sphere, so it's going to be a circle. We know that that's the property of this entire cross section and of a sphere. So a cross section is always going to be a perfect circle, as shown in this drawing. And what we're going to have to do is we're going to have to calculate the given area of that given cross-section with one piece of information, only one, and that's that our radius equals 4 yards. That's all we have. We have to calculate the area of our circle. You might be extremely scared here, but it's also simple because I'm also going to give you another piece of information about the relationships between the circle and the sphere. So we know that this distance right here, so this is the distance between the center of the circle and the center of the central circle of the sphere. So this is the center of the sphere, and this is the distance between the center of this cross-section circle and the center of the sphere itself. So the distance I'm going to give you is going to be another 4 yards. Sorry, not 4 yards. I apologize. 2 yards. So this is going to be 2 yards. So doesn't that kind of spark something inside you like, wait, this is exactly what we did for the pyramid problem. And yes, that is exactly what we're doing here. So we know that the entire distance from the circle all the way down to the very bottom or any point here. So this entire distance here from top to bottom of the sphere is going to be equivalent to the radius itself. So that's going to be 4 yards as I've shown you above right here. So we know that this is going to be 2 yards below the given center. So that's going to be half the distance of the radius. So we know that 2 yards over 4 yards is going to be 1/2. So 1/2 is what we're given equals 2 yards over 4 yards. When we're given that information, all you have to do is take the central area of the circle, calculate what the area of the circle is itself in terms of pi, and then merely just divide it by 2 to get the area of the cross section. So what we're going to do is we're going to calculate that. So we have our radius here as 4 yards. So we're going to do pi r squared to find the area of our central circle, central circle being the central circle of the sphere. So we're going to do pi r squared. So pi times 4 squared equals 16 pi. Leave it in terms of pi to make an exact answer. We're always here for exact answers. And then, of course, 16 pi, all we're going to do is divide 16 pi by 2 to get an answer of 8 pi yards squared. And that is all for our cross-section practice. Now onto the much easier, much more of a favorite of mine, the object generation. I love explaining that topic, and I hope you really get a lot from this. It's a very unique situation. Not a lot of geometry courses actually look through cross-sections separately, but I'm here to extensively look through these properties because I guarantee you they're going to be on your SATs, ACTs, final exams. Something that they don't necessarily look over is not necessarily going to be overlooked. So it's very important that you look over these essentials that you might not necessarily might not necessarily look through in the classroom. So let's move on to rotated figures, and I promise you we're almost done. So practice with rotated figures part 1. We're going to name the properties of the rotation. So we're going to start off with a basic triangle. Of course, it has side lengths 4, 5, and 3. It's a right triangle as indicated, and it has points A, B, and C, sides A, B, BC, and AC. All we're going to do is we're going to take this given triangle and we're going to rotate it across an axis. In this case, we're going to be moving in a negative manner. So we're going to be moving, we're going to be moving in a positive manner, which is clockwise. So we're going to be moving clockwise direction, and that's going to be a full 360-degree rotation around this given axis. So what it's going to do is it's going to take your triangle, it's going to rotate all the way around and meet up back again at that same exact point it started, or the same exact position it started. So when you do that, you're taking this triangle and you're rotating it all the way around 360 degrees. And when you're doing that, you're actually forming a circular motion when you're doing that. And when you're doing that, you're going to form circular sides of your given shape. And what this is actually going to form is a cone. And what are some properties that this given triangle inherits? I mean, this given cone inherits from this triangle, this right triangle. Well, as you can see here, the direct altitude of your cone is going to be the same exact altitude of your right triangle. So altitude is going to be the same. And then, of course, we have our hypotenuse. But in terms of a cone, it's going to be your slant height. So your slant height is going to be the same. And then what's the length of your base, meaning the radius of your given base circle of your cone? That's also going to be equivalent to the base of your base radius. It's going to be the same exact as your base of your right triangle. So it's going to be the base radius is also going to be the same. All right. So those are some similarities I really wanted to show you. I'm going to show you one more example And then, of course, that'll be it for today's video. So practice with rotated figures part 2. We're going to name the properties of this rotation as well. So let's take a look at this circle here. We're given some values such as our radius equaling 2, and then our distance from the given line to given axial rotating generating line from the center of the circle being 4. We're going to rotate it around, same manner, 360 degrees clockwise, so it's going to be a positive 360-degree rotation. And when we do so, we end up with this value. So this little model here shows exactly what's happening. It's rotating across this entire axis, and when it's doing so, this axial axis is rotating across. And when it rotates across in that same manner, it's going to form something that looks just like a donut. I wanted to show you, that looks exactly like a donut. But there's some very common properties in this whole entire transition. So what are some things that it actually inherits? So there's relationships between volume and area, and I'll get to that after I go through the similarities of the dimensions. So we see that our radius equals 2. The radius of this entire central donut is also going to equal 2, so the radius is the same. The distance from the center of the shape is also going to be the same. So the center right here, the two centers are going to be the same. So distance from center is going to be the same. And what are some relationships that we see here? So we know that with our radius equaling 4 and with our radius equaling 2, we can calculate, pi r squared. So it's going to be 4 pi is going to be the area of this circle right here. But something that we know is if we can calculate since we know we're rotating 360 degrees, technically we're rotating with 360 different circles being placed on top of each other with the same area. So in essence, this would be a certain degree rotation that's going to be multiplied by that given 4 pi. We don't exactly know what that value will be, but I will get into that in our sometime later in this geometry course. I want to explain to you how exactly we can calculate that. But all I want you to see is that we're actually doubling up these circles on top of each other with every certain amount of motion, and that's where radians actually come into play. All right, everyone. So that'll be it for today's video. I hope you guys enjoyed. This has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe down below at our YouTube channel. And please make sure to hit that post notification bell right next to the subscribe button so you don't miss out on any of our channel's latest uploads. Please feel free to utilize that comment section down below. We really do love your feedback and your constant flow of communication with us and interactiveness. We will reply, of course, and we will implement any of your constant feedback in our videos to come. Also, check out our website at www.ecoreacademy.org. We're really proud of how that turned out, and it's one of our best products out of eCoreAcademy Learning Platform. It's a full package of what we actually offer. It has integrated quizzes, note sheets, and worksheets that go along with each and every single one of our videos, organized into their own separate course studies just for you. All you have to do is make an account for free. Feel free to email us at ecoreacademy@gmail.com. Full email will be in the link in the description down below. You can email us if you have any questions or if you just want to reach out. And finally, check all the socials down in the description box below. Full link is accessible there at Facebook, Twitter, and Instagram. See what kind of content we have there and use our mediums to share all of our videos. Once again, everyone, I hope you guys enjoyed this video. This has been AJ, and I will see you guys in the next one. Peace.